A very good morning to all my dear panels. My name is Deevager Tanabal. My matrix number is B0517100086. I am from 4 BMFG 3 section 2. My supervisor name is Dr. Zaleha binti Musafa. Today I am going to present about mechanical performance of treated pineapple leaf fiber reinforced epoxy composite. Chapter 1 Introduction. There are 4 subtopics in this chapter, which is Introduction on Study, Problem Statement, Objective and Scope of Study. Now, introduction. Nature fiber has variety of uses as reinforced, especially in composite materials industry. Because of its moderate specific strength and stiffness, pineapple leaf fiber is one of the best significant plant-based fibers for composite materials. According to the Garkil and Malkapuram, nature fiber composites offer numerous advantages compared with the glass fiber composites, including their lightweight, biodegradability, ease of machinability, lack of toxicity, low cost, non-abrasive nature, and availability. Many researchers have been emphasized about global warming and environmental pollution. As the issue have become more serious, nature fiber with reinforced composites can help to overcome these problems. Problem statement. The issue of global warming and environmental pollution are being addressed by many researchers. Natural fiber reinforced polymer composites or green composite could help to solve this problem, stated by Palani Kumar. Natural fiber has a better properties than synthetics on, such as a low weight and cost, easy recyclability, biodegradability, abundant availability. Natural fibers have accepted mechanical properties stated by STB. This study can be utilized to produce a strong and better composite, particularly in effort to incorporate natural fiber as a way to combat environment issue. There are two objectives in these studies, which is to evaluate the effect of the fiber loading onto the physical and tensile properties of the pineapple fiber reinforced epoxy composite and to compare the experimental and theoretical properties of pineapple reinforced epoxy composite. Scope of the study. The natural fiber will be alkalinely treated and embedded in epoxy resin using hand layup process. The composite will be prepared at different fiber loading, which is 10%, 20%, 30% and 40%. The composite then will be characterizing physically, which is density measurement, and also mechanically tensile testing, and also the comparison between theoretical and experimental method. The rule of mixture will be used for the theoretical method, while the secondary data will be used for the experimental method. Chapter 2 Literature View. In this chapter we are going to discuss based on the previous journals and articles and also the previous knowledge and understanding related to the study. Now, literature review. These are the articles that helped me to do the research. By these articles, I used to learn how to use the rule of mixture to find out the properties of my composites. The findings of the articles helped me to do the discussion about the results that I have made from the theoretical experiment. Chapter 3 Methodology. This chapter explains on the project development of the specific technique used to implement this project and also discuss the details of procedures and method used to conduct these studies. This is the flowchart of the project. First of all, start and prepare the pineapple leaf fiber from Sarawak. Alkalinely treatment for pineapple leaf for 24 hours under 60 degrees Celsius and fabrication of the composite using mold. Cut the composite according to the sample size using bandsaw. The mechanical properties testing for the treated pineapple leaf fiber with epoxy resin. Determining the value of physical and mechanical properties using rule of mixture. Physical characterization. In the physical characterization, we have identified the density by using machine ASTM D7009. These are the formulas to find out the physical characterization by using the rule of mixture. For density is 1 over weight of fiber over density of fiber plus weight of matrix over density of matrix, and to find out the white content, density of theoretical minus density actual over density of theoretical. There are two types of mechanical characterization we found out, which is tensile test and Young modulus. For the tensile test, there are two types of formula for experimental method and theoretical method. For the experimental method, maximum force at break divide area of fiber cross section, and for the theoretical method, tensile stress of composite equals to tensile stress of matrix product with volume of matrix and plus with tensile stress of fiber product with volume of fiber. For the Young modulus, there is only one formula for theoretical, which is Young modulus of composite equals to Young modulus of matrix product with volume of matrix and plus with Young modulus of fiber and volume of fiber. Chapter 4, Results and Discussion. The results that are obtained from the study are analyzed and presented in the terms of tables and graph. The graph makes the comparison easier, and the data and results are discussed to achieve the objective and obtain the conclusion. Now, physical properties, which is density. The density of the composite depends on the relative proportion and reinforcing materials, and this is one of the most important factors determining the properties of the composite. The difference in the theoretical and experimental densities is mainly due to the presence of the white in the composite. Hence, it becomes essential to determine the percentage of whites in the sample prepared. The experimental and theoretical densities along with the corresponding volume fraction of whites in pineapple leaf fiber composite were presented in table. White content of 40% of composite show the higher white. This is because the additional in the pineapple leaf fiber loading was attributed to the poor fiber or matrix bonding and ultimately to incomplete wetting of pineapple fiber by the epoxy matrix. In this table, it shows that the white content of composite increasing with the increasing of pineapple leaf fiber loading. This is because natural fibers consist a lumen in its cellular structure which act as a white. It means such a fiber carries these whites naturally. Thus, it may the reason of increase in white content with the increase in fiber loading, which is stated by J.P. Dahl and S.C. Maris. The presence of the white in the composite significantly affect the mechanical properties directly or indirectly. Mechanical properties, which is tensile strength. From the table, it can be seen that 40% of pineapple leaf fiber loading of experimental and theoretical show the highest value of tensile strength and strain in the range of 63.8 and 76.44 megapascal respectively. This is because greater the fiber loading will be enhancing the strength of the composite. The function of the matrix is to transfer the force to the fiber. Hence, if the fiber loading has been increased, it can withstand higher force compared to the lower fiber content, which is stated by Matthew and Davis. Tanabal stated that good adhesion between the fiber and matrix make it feasible for stress transfer to take place from the matrix to the fiber, thereby improving the strength of the composite in a natural manner. Improvement of the tensile strength due to the addition of fiber content will have the effect of reducing the strain properties. Comparison of the experimental and theoretical values for the tensile strength in this table shows that the tensile strength increases with the increment of pineapple leaf fiber loading. However, the experimental values are lower than the theoretical values. This is because the fibers were not perfectly aligned or composite were poorly prepared. Now, Young modulus. From the table, it can be seen that 40% of pineapple leaf fiber loading of experimental and theoretical show the highest value of Young modulus in the range of 15.42 and 17.44 gigapascal respectively. At the 10% of pineapple leaf fiber loading, the value of experimental is higher than the theoretical. This is because of the good addition of fiber composite with the matrix in experimental method, stated by Tanabal. From the figure, both experimental and theoretical method increase with the increment in fiber loading of composites. By Davindra Madhivanan and Januar Parlagavan suggests that the higher fiber content, a weak interface was created due to the increase in fiber to fiber interaction. The fiber were not perfectly aligned with matrix white and dispersion problems. But in this study, maybe the good addition of pineapple leaf fiber with the epoxy makes the young modular stress increase with the increment of pineapple leaf fiber loading in these composites. Finally, conclusion. The result obtained shows that the 40% of pineapple leaf fiber reinforced epoxy composite shows the better mechanical than 10%, 20%, 30% pineapple leaf reinforced epoxy composite as the percentage of the fiber content increases to both experimental and theoretical method, which is 76.44 MPa and 17.44 GPa. The white content in 40% of pineapple leaf fiber reinforced composite shows the higher value in both experimental and theoretical. This is because the natural fiber consists of lumen in its cellular structure which act as a white. It means such a fiber carries these whites naturally. It also discovered that distribution of the fibers is not precisely aligned, which has an impact on the mechanical character of puff reinforced epoxy composite. Thank you.